Hello, in this video we will talk about a very important data analysis procedure. It is called principal components analysis, or PCA, and show how to carry out an PCA with R. So principal component analysis is a data reduction technique. So it will transform a larger number of correlated variables into a smaller set of uncorrelated variables. So we see this figure. This is, for example, there are 5 variables, and in reality maybe more than 5, maybe 10 or 20 variables from a data set. Because these variable numbers are too many, so we hope we can extract information and create several principal components, and these are linear combinations of these variables. So we call it PC1, PC2, and so on. And these principal components are not correlated, and they capture as much variance as possible from original data sets. And these weights, for example, PC1 is A1, X1, A2, X2, plus 2, AK, XK. These X are original variables. And these weights are selected. The criteria is to maximize the variance each principal component accounts for, while keeping the components uncorrelated. So PC1 is not correlated with PC2 and not correlated with PC3. They are orthogonal. They all are orthogonal. Although the original variables may have correlations from one another. And usually, the first principal component is the weighted combination of the k observed variables that accounts for the most variance in the original variables. So the first component, called PC1, they capture the largest part of the variance. And the second principal component is the second, capture the second largest of the variance from the remaining variance after principal component 1, and so on. For example, principal component 1 capture 80% of the variance from the original data. Then principal component 2 capture 15% of the variance from original data sets. So these two principal components, they capture total 95% of the variance from original data sets, right? Then principal component 3 may capture 3% of the total variance. So these 3 principal components in total capture 98% of the variance. So if we are satisfied because they capture as much variance as possible, so we just use 3 principal components. Of course, if you add more many principal components, it's meaningless because we just want to make a principal components number as few as possible, right? Otherwise, we can just use original variables, right? And how to implement a principal components analysis. So first we will decide how many components, or say how many factors to extract. Then we will extract these components. Then we will rotate components and interpret the results and compute components or factor scores. But these later factors is related to another kind of analysis called exploratory factor analysis. We will focus principal components only here. And in the next video, we will focus on exploratory factor analysis. So next we will show an example with R doing principal components analysis. So the dataset called US Judge Ratings contains lawyers' ratings of state judges in the US Supreme Court. and the data frame contains 43 observations on 12 numeric variables. And from a practical point of view, can you summarize 11 evaluative ratings? Here 11 because we just use 11 variables here. One is not related, and with a smaller number of composite variables. If so, how many will you need and how will they be defined? So the question is very clear. We want to decide how many principal components that we can use to from these 11 variables, right? And so step 1 is selecting the number of components to extract. And in practice, there are several criteria that you can use to select how many components. And basing the number of components on prior experience and theory. And the second is select the number of components needed to account for some threshold cumulative amount of variance in the variables, for example, 80%. So if, for example, 2 components can capture 80%, then we just use 2 principal components. And the third is selecting the number of components to retain by examining the eigenvalues of the KK correlation matrix among the variables. Because principal components are directly connected with the eigenvalues of the matrix. This matrix is K times K correlation matrix among the variables. So the most common approach is based on eigenvalues. And each component is associated with an eigenvalue of the correlation matrix. So each component is connected with an eigenvalue of the correlation matrix. Because correlation matrix is by the variable number is a square matrix, right? Then this square matrix has the number of eigenvalues equal to variable numbers. But we do not need so many eigenvalues. We just need the first 2 or first 3 or maybe first 1 eigenvalue. So the number of eigenvalues we used is the number of the components we want to use. And the first principal components associated with the largest eigenvalue, and the second principal components with the second largest eigenvalue. It's quite clear, right? And there are several criteria that we can choose the number of principal components. One is called Kaiser-Harris criterion. This suggests quite clear that the components with the eigenvalues greater than 1. So we only choose the eigenvalues greater than 1, then from these eigenvalues we can choose the components, principal components. And another criteria called Cartel screen test. So this screen test will show the eigenvalues plot against the component numbers and show there is a bend or elbow in the figure. So we only choose the components with the eigenvalues that above this sharp break. Above this sharp break, we will show this figure later. And another criteria called parallel analysis. So this is based on simulations. It will run data matrix with the random data matrix of the same size as original matrix. And from this simulation data, there is a dashed line in the figure, and we choose the eigenvalue from the real data is larger than the average corresponding eigenvalues from the simulation. So next, we will show which package is used in R. So here we use the package called psych. So you have to install this package in R, so PSYCH. Then the first function is FA parallel. Here F is small capital, is small letter, right? FA not capitalized. So FA dot parallel. We will show first load this package. And we use the function called FA parallel and US judge data. We use the first to 11th variables, then use the FA called PC. Here use the PC because principal components, and with iteration 100 because we want to simulate the data. Then show legend the false, and the main is the label, title, and we also add a horizontal line with 1 because we want to show which eigenvalue is larger than 1. So run, and the figure comes here. We show this plot. So here is the 1 line here, horizontal, and we show only 1 eigenvalue larger than 1. So from the first criterion, right? The second is the band. Band also from here band, so we will show eigenvalues above this band, also only choose this one. And the third criterion is from the simulation. This is dashed simulation line. And we show the eigenvalue above this dashed simulation line. So also this first eigenvalue will be selected. So all the 3 criteria tell us that we have to choose only the first eigenvalue in the components. So after we have decided how many principal components we will extract, the next step is to use the function to extract these principal components. The function in R is principal from psych package. This will perform a principal components analysis starting with either raw data matrix or a correlation matrix. So the format is principal R, n factors, and rotate and score. So here R is a correlation matrix from the data or just a data matrix. And n factors specifies the number of principal components to extract. So default is 1. And the rotator indicates the rotation to be applied. So value max by default, and the scores specifies whether to calculate principal component scores, and the false by default. So next we will show. So here we use a principal and this data frame with only 11 variables and n factors 1. So others only use default. Show these principal components. Here we can see all the variables, original variables, and PC1. Here, this is the parameters that PC1 principal components with these variables. Because principal components is a linear combination from these variables, right? And H2 will contain the components commonalities. Commonalities means the amount of variance in each variable explained by the components. So we look at here, this column H2 means the principal components explain the variance of this variable. So for example, these variables, 84% of the variance explained by these principal components. And U2 column contains the component uniqueness. So the amount of variance not accounted for by the components. Actually, this is equal to 1 minus H2. So here U2 is 1 minus H2, which means this variable, about 16% of the variance not accounted for by these principal components. If we use more principal components, so this U2 will be less because more components will explain more variance, right? And next is SS loading. This is the eigenvalues associated with the components. So here SS loading. So this is the first principal components. If we look back, the figure we have shown, you can see the first principal component is much larger than the rest. So the first is about 10. And proportion variance explained in total of this data set by this principal component is about 92%. And we will consider second example because in the first example there are only one principal component extracted, and we use the second example. This comes from the data called Harmon 23, and this is the correlation matrix for the input, and observations is 305 goals. So next we will show this data, how to do these examples. So we just load and set the seed, and here we use the first function FA parallel, right? Then this is the correlation matrix COV covariance, and we have to set observations number 302 here, and principal components and simulation 100. The next is the same as before. Then run. And see, if we take a look at this figure, you can see this data sets the best how many principal components we have to extract is 2, because only these 2 larger than 1, and over this simulation data, this line, right? So we will decide to extract 2 principal components in this example. And next, same as before, we will calculate these principal components using principal function and correlation matrix and n factor 2 and rotate none. Then we show this resulting column principal 1, principal 2, their loadings, their parameters with these variables, and H2, U2 here, you can see about 80% of the variance for this variable explained by these principal components, right? And about 12% of the variance not explained. And as is loading, the first eigenvalue is 4.67 and the second is 1.77, and their total variance explained by these principal components is the first is 0.58, second is 0.22. So in total, about 81% of variance for this data set explained by these first 2 principal components. After we have performed which calculating the principal components, the next step usually will be rotating principal components. This only applies to the case where at least 2 principal components exist. So in our examples, in the first example, there are only 1 principal component, so we do not need to do rotating. And in the second example, there are 2 principal components, so we have to do the rotation, which is a mathematical technique to transforming the component loading matrix, which is more interpretable. So it is easier to explain what's the meaning of these components. And rotation methods will differ. One is called orthogonal rotation and another is called oblique rotation. So orthogonal rotation will result in the components remain uncorrelated, and oblique rotation will allow these components rotated. So we cannot call these components after rotation as as principal components, because this is not principal components anyway, because principal components is only before the rotation. So after rotation, there's only components, not principal components. So we will show example later. And for the most popular rotation, this is the orthogonal rotation. So for this rotation, there's a method called variance. Variance means to make the loading matrix for these final components by a limited set of variables. So which means we can make components, for example, the two components, each has most corrected with some original variables as possible. And other components may be connected with other variables as possible. So this makes us easier to explain what the components are. So in our example, we just use principal function same as before, but here we will add variance in the rotate, not known. In the last we use known, but here we use variance and factor 2 and with this correlation matrix as input. Run, and here we show the results in RC. So now you can see this loading matrix column is RC now, because this is after rotation, but same as the two components, but they are not principal components now. They are two components, and their loading coefficients, and you can see the first component has larger parameters with these variables. So these variables are height, length, arms, span. They are mostly the length variable, for the body length variable. And the second components have very large coefficients connected with weight, chest. So these components may be called volume components. So the first component is a length component. Second is a volume component. And their H2, U2 of course, also they are the same as before. How much variance explained. And if we look at this loading, these RC when they are SS loading are not the same as before, because they are not eigenvalues now. And the total variance explained is 0.81, but the division for each components are not the same as before. Again, so here is 44% for the first component, and the second component is 37%, but the total variance from the data explained by these two components are the same as before, 81%. And the last step is to obtaining the principal component scores. Scores means we will create a new variable. New variable is the components or principal components. They are coming from the original variables, but we use only 2 or 1 principal components to represent the original 11 variables, right? So in the first example, we show, because the original data is the input, so we can create scores, right? And we just use principal, this data frame, 11 variables and 1 components, and with true for the score. Then we show several scores. You can see this is for the column called principal components. So this is a score, and we only show the first 6 scores. And in the second example, because the input is only for the correlation matrix. We have no original data frame, so it's not possible to create the principal components for these variables. But we can get the parameters which we can calculate the principal components. So same function here, we use variance and factor 2. We show and int results for the RC, we take the weights variable. So this is the weights for the parameter coefficients, which can be used to calculate the components 1 and components 2 from other variables. Here 8 variables. So for example, this is not principal, the components 1 is the variable 1 times 0.28 plus variable 2 times 0.30 and so on. And the components 2 is variable 1 times the minus 0.05 plus variable 2 times minus 0.08 and so on. Because we currently have no original data frame, we have only correlation matrix, so it's not possible to calculate directly the principal components. But we have weights. If one day we have original data, we can use these weights to calculate the principal components, right? Thanks for watching.